Good morning and good afternoon, everyone. I'm Ryan Felton from the exobiology branch at NASA Ames Research Center. And today we're continuing and finalizing the education series we begun for AIML about 2 weeks ago, where Dr. Floyd Nichols from the Department of Geosciences at Virginia Tech did part one on unsupervised learning. And today we'll be completing it with supervised learning. And we'll have any questions or anything, just save them to the end, and we should be able to have some time, but we're going to go right into it. Floyd, take it away, please.
Great. Thanks so much, Ryan. I'm going to attempt to share my screen here. Can you let me know if you can see it?
It's good. Go for it.
Great. Okay, so welcome back, everyone who participated in part one of the series. And if you are just now joining, well, welcome, and hopefully you'll get something really good and interesting out of learning about supervised learning, which is what this presentation is going to focus on. So before I talk about supervised learning, I just wanted to take a step back and think back to the last time we were all together for part one of the series, unsupervised learning. One of the first things that I asked during that presentation was, what AIML techniques do you know about? And we got sort of a list of a few different algorithms. Some of the most well-known ones were PCA, regression in general, as well as random forest. And what I thought was interesting when I was looking at this word cloud was that most of the methods that people mentioned were actually unsupervised learning, such as PCA, clustering, K-means, deep learning can kind of fill both unsupervised as well as supervised. But there was much less uh, knowledge around the supervised learning, whether it's regression, linear regression, or even some different classification methods as well. And so I'm going to talk a bit more about that today in this talk. And so I also wanted to go back to this figure here, one, because I really like it, and I think it just describes the breadth of different applications of machine learning and artificial intelligence. And last time we focused on this small branch of machine learning, unsupervised learning. But today we're going to focus a bit more on supervised learning and a little bit of deep learning. And the reason why I say a little bit of deep learning is because deep learning is kind of interesting in that it can be used for a variety of things within the field of machine learning, including supervised, unsupervised, semi-supervised. And I'll talk a little bit more about sort of the differences between those and how we actually identify that in the world of artificial intelligence. So what exactly is supervised learning? Well, the last time we were together, we learned that unsupervised meant that there was no human intervention required to analyze your data. However, supervised learning, as the name suggests, is defined as the use of labeled datasets to train algorithms to classify data or predict outcomes from data. And there are a few different use cases that we tend to use supervised learning for, and that includes classification as well as regression. And I'll talk a bit more about what that actually means later on in this talk too. But these are the two primary cases that we use supervised learning for. And I wanted to show this pictogram here from Dupont et al. In 2023. One reason is because I really, really like the way that they describe supervised learning. So I also encourage you to read this paper if you are interested. But you can see here that as they describe, your data set is divided between features. We can think of that as a matrix of numerical values, maybe even categorical values, and then labels. So the labels is where the human intervention comes in. So this is where we define and we tell the algorithm that this is equal to this. Unlike the unsupervised learning that we learned about last time, supervised learning requires the use of training your samples and training your data to make predictions. And so in this way, the model actually can learn over time. And again, I'll discuss that a little bit more later in this talk as well. But yes, the ultimate goal, whether it's classification or regression, is to make predictions about your data. So unsupervised learning, our ultimate goal was really to understand the structure of our data and maybe discover some hidden patterns. But here we actually want to make predictions. So that's one of the things that sets supervised learning apart. So supervised learning can be further subdivided, sort of as I alluded to just a little bit ago. We can think about traditional machine learning, which, again, as I just described, seeks to classify or regress problems, so classification or regression. But we also have deep learning as well, which also seeks to do classification or regression as well. So there are some key differences between traditional machine learning and deep learning. And if we look at the top portion of this figure on the bottom left, we can actually see this a little bit more clearly. So in our classic machine learning or traditional machine learning approaches, uh, we have some element of our data, our input data. We extract some features or we identify features. We generally call this feature engineering in machine learning. And this is going to be where expertise comes in from a human perspective. Then we train that data from our features that we classify, and then we get some prediction. Deep learning, on the other hand, is a little bit different in that we can take that same input data and we can actually bypass feature extraction or feature engineering. And the model will actually learn everything on its own and it will extract its features on its own as well and produce some output. And so there's a little bit less human intervention associated with deep learning. So one important thing to note, though, is despite being able to perform the same functions, traditional machine learning requires this feature engineering, whereas deep learning does not. Even though we are not requiring feature engineering, and it is important to note as well that you can employ feature engineering in deep learning, but it is not necessary. Uh, and even though we are not including this feature engineering, feature extraction, these architectures are generally a lot more complex. And that's going to have some implications. So you might be scratching your head right now and thinking, well, okay, he just told me that traditional machine learning can do classification or regression problems, and well, deep learning can also do classification and regression. And why might I care if I need to employ feature engineering or feature extraction or not? And so we kind of come to this problem of, oh, do I choose classic machine learning or do I choose deep learning? And well, there's actually a way to uh, decide which methods we should employ for our own data. So we can think about this figure here, which I really like, um, in which we have on the x-axis the amount of data from whichever samples you're collecting, for instance, versus the performance. This performance could be anything, for simplicity, let's just say accuracy of a model. So amount of data on the x-axis and performance on the y-axis. So you'll notice that there's different behaviors going on in this graph. Let's first take a look at the traditional machine learning. We see that there is a sharp increase and then it sort of plateaus, maybe let's just say this is 1,000 data points. And then there's not much improvement afterwards. On the other hand, if we look at deep neural networks, there's sort of an exponential growth and the performance seems almost limitless. And so that's one important thing to think about when deciding on your model. And so whether you're familiar with machine learning or not, you might have noticed in the past few years that uh, neural networks, especially deep neural networks, have garnered a lot of attention. However, especially in the world of astrobiology, that is not always the preferred or even best method. So if we look at this figure again more closely, let's say that this number here, where my mouse is 1,000 data points. That's generally considered small for machine learning. Well, we see here that if you're working with small data sets, as astrobiology tends to be, traditional machine learning methods are actually going to have much better performance than deep neural networks or medium neural networks or even shallow neural networks due to the fact that they require larger amounts of data to actually achieve their best performance. However, if you are working with large data sets, well, we can see here very clearly that neural networks are going to outperform, generally speaking, traditional machine learning methods. And there are other cases too that I'll discuss briefly later, in which maybe your data is not large, but maybe you're working with images, for instances. Well, neural networks may perform a bit better as well. But one of the things that we want to think about is, okay, as performance increases and as the complexity of our models, we can think of traditional machine learning models as perhaps not as complex, and shallow neural networks as more complex than traditional, but not as complex, and the most complex being deep neural networks. Well, because they require more data and their architectures are a lot more complex, it's going to be computationally very, very expensive. So that's another important aspect to think about when you want to apply supervised machine learning to your own data, is how much computational power do I have or do I actually need? So let's talk about what regression and classification is. So many of you are probably already familiar, but for those who are not, let's talk about it briefly, just so we're all on the same page. So regression is a technique used for investigating the relationship between independent features or variables, which we might know them as, and dependent numerical outcomes. So specifically, regression is used to make some prediction about numerical outcomes and numerical outcomes only. So here on the x-axis, we can think of some numerical features or feature, and then on our y-axis, our predicted outcome or variable is going to be numeric as well. Classification, on the other hand, is defined as a process of recognition, understanding, and grouping of objects and ideas into human-defined categories. And the reason why I say human-defined is unless we're doing a semi-supervised learning approach, which I'm not going to talk about today, in which you employ unsupervised and feed that into your supervised, here we actually have to define it, the scientist. And unlike the regression, where we've got numerical features making predictions about numerical outcomes, with classification, we might have a mixture of numerical features, categorical features, and we want to predict something that is non-numerical and categorical in nature. So in this case, we can say squares versus circles. So those are the two key differences between classification and regression. So depending on what you're working with and what your data looks like, you might want to apply regression, classification, or perhaps both, which some people do. It's important to note as well that most algorithms can perform both regression and classification, which is very handy if you don't want to switch algorithms. However, there are some exceptions to this, of course, and I won't talk about all the exceptions, but if I come across a model in the later descriptions, I will let you know if it is primarily used for classification, regression, or if it can be used for both. So now that we have sort of a background on what classification is, what regression is, what supervised learning even is, let's talk a little bit about some of the traditional machine learning algorithms. So one of the most basic, although I don't maybe don't want to use the term basic because when we're thinking about these supervised learning algorithms, they're actually quite complex still. But in the world of supervised machine learning, logistic regression is a relatively simple one to understand. Um, and despite its name, logistic regression, this is primarily used for classification. And I won't describe why that is exactly. However, if there are questions later, I can delve a little bit more into why this is called a regression, even though it's used for classification. But as we can see here, logistic regression uses a sigmoid function. And again, you don't necessarily have to know what this is, but just know it's this S-shaped curve here that we see to convert predicted values into probabilities. So on our x-axis, we usually have some features, and this can be whatever it is that your data set is. And on the y-axis is going to be values from 0 to 1. So logistic regression values are always going to be between 0 and 1. And whether or not your data falls along, say, this line, 0, it will have a predicted class A. And if it falls along the line 1, it's going to have a predicted class B. Well, you might be asking, well, what if I have points that don't necessarily fall in these lines and maybe I've got a point here? Well, with logistic regression, because these numbers we can think of as probabilities, if we define a cutoff point, say maybe 0.5 or 50%, we can decide if it's over 50%, it belongs to class B, and if it's under 50%, it belongs to class A. So because of this simplicity and the fact that it works very, very well with linear separable data, logistic regression is an algorithm that is kind of preferred actually when you're thinking about linearly separable data because of the fact that it's very interpretable and explainable. K-nearest neighbors, on the other hand, is a little bit different. And actually, you might notice that this has some similarities to the K-means clustering algorithms that we discussed in part one, although this is a little bit different. The similarities in their names, K, really come from the terms that are used in their mathematical equations. But anyways, K-nearest neighbors is quite interesting and can be useful, especially when you're working with, say, spatial data or data that you've clustered, is it uses proximity to make classifications or predictions about the grouping of an individual variable. So we can take a look at this GIF here on the left, and we'll wait for it to go back to small here. So looking at this white point, the way K-nearest neighbor works is you first define a K value. In this case, in this GIF, we're incrementing it to actually decide which one's the best to use. But this K value indicates the number of neighbors for your point. So in this case, let's wait for it to go back, actually. So when K equals 1, we have exactly one neighbor. When K equals 2, we have two neighbors. When K equals 3, we have three neighbors, and so forth. And the way that this algorithm works is it basically uses a majority vote. So when K equals 4, or K equals 5, this is a better instance. When K equals 5, green was equal to 2, and red is equal to 3. So because of that, we will say that this point belongs to the red class. So much like the logistic regression, K-nearest neighbor is very easy to understand, very interpretable. But you can see here from this GIF to the left that a big disadvantage of K-nearest neighbor is you have to have a predetermined value of K. And depending on what K is, your answer is going to be very different. When K equals 1 or 2, our point is equal to green. However, when K equals 5, our point is equal to the red class. So there's a lot of hyperparameter tuning that is required in K-nearest neighbor. However, once you define the optimal K for your data set, this can be really powerful, and especially because it's easy to understand. So now we start to get into algorithms that are a little bit more, say, esoteric and maybe a little bit less easy to understand, although in this particular case here that I'm showing, it perhaps is a bit easy to understand. But we can think of two classes being separated in some space. In this instance, it's a two-dimensional space. And the way that support vector machine actually works is it classifies data by finding an optimal line or hyperplane that maximizes the distance between 2 points. So you see here, we've got our green point and we've got our red point. And using some optimization, the support vector algorithm finds the line that maximizes the distance between this point and this point from class A, we'll say, or class green and class red. And in this case, we can say that any point that falls along this line, we'll wait for the line to come back, but any point that falls, let's say, to the left side of this line, we'll consider this to be in the red classification. And any point that falls to the right side of this line, we'll consider to be on the green classification. And you'll notice that much like logistic regression, the standard form of support vector machine works very well with linear data. And additionally, it's really effective in cases where the number of dimensions is greater than the number of samples. And that's primarily because of how the math works out for this particular algorithm. And one important thing to mention for support vector machine is if you are using standard support vector machine, generally it doesn't handle nonlinear data very well. However, if you recall from our kernel PCA that we talked about last 2 weeks ago, we can actually employ a very similar trick for support vector machines called the kernel trick. And it's a bit difficult to actually show visually, but rather than using a line or a plane to separate your data, you can transform your data and use nonlinear methods like polynomial functions or a radial basis function to actually create some hyperplane that separates your data in high dimensional space. But if you recall from the last time we talked about unsupervised learning and even earlier today, the more linearities you add, the more complex and more computationally expensive it is. So if you do have data that's linearly separable, then you might want to stick with standard support vector machine. However, if you have more nonlinearities, you might want to think about increasing the computational power and complexity of the model. And another very important and very popular supervised machine learning method, more specifically for just traditional machine learning, is random forest. And this is a method that people seem to know about in the last word cloud that we had for the unsupervised portion. And the best way to think about a random forest is it's a series of decision trees. So we can focus on tree one for now. And the way it works is you have this node, and at this node, you've got some, say, decision to make. And in this case, let's just make something up. And let's say, is x greater than 5? If the answer is yes, we're going to go down to this node. And if the answer is no, we go here. And we can keep going and making decisions like that. Is x greater than 7? Yes, go left, and then no, go right. And you can these decisions can go on for, as long as you tell it to, or as to tell the model to. And in a single decision tree, you'll get one answer. So in this case, A. However, we know with very complex data, maybe your decision tree chose decision boundaries that might not be that great. So one of the utilities of random forest is it's technically an ensemble model because it takes these series of decision trees and makes a prediction, and the majority vote is what the actual prediction becomes. So in this case, we have two trees, tree one and tree two, voting A or making a prediction of class A, whereas tree N, we'll just say tree three, makes a prediction of class B. Well, because class A is a majority vote, then it becomes the actual prediction that we make. So this is really nice because in some ways, the random forest does an automatic cross-validation, which you often have to do manually for other algorithms. So like support vector machine, if you have data where your number of dimensions is greater than the number of samples, this is really effective for that. And thinking about astrobiological data, this often is the case where we've got maybe, say, 30 to 40 variables, or maybe even 100 variables, and you only have, say, 20 samples or something like that. So random forest and support vector machine are generally going to be really good if you're working with low data sets and high dimensions. And again, like the, say, kernel trick for a support vector machine, this can be very extremely effective for nonlinear data. However, as all things nonlinear, very computationally expensive. So how about deep learning? So we've made this distinction between traditional machine learning and deep learning. Well, deep learning is quite fascinating. At least I think it's fascinating because it's a method in machine learning that teaches computers to process data in a way that is inspired by the human brain. And what I mean by that is, if anyone here has taken biology class, or maybe you haven't, and you don't want me to talk about biology, but unfortunately I have to anyways, is the neuron. And you might be familiar with neural networks, but in the human brain, we've got neurons that have different parts, including dendrites, the cell body, and axon terminals. Well, the way that neurons work is, say the human brain is processing information. It has these inputs into the dendrites. It tells the cell body what that input is, and then this information is passed along to the axon, to which you've got some output for the axon terminals, and this can propagate for however many neurons there are in your brain, and we can then perceive that as some information. And so deep learning works in the same way, where you've got your inputs, and we can think of these as sort of dendrites. We've got our bias functions, um, which you can think of as your cell body, and this is going to tell you when to activate something or when not to activate something. And then you've got your output. Was X activated or was X not activated? And from there, we can process our outputs. And let's just say in this case, class A, class B, or class C. Um, More specifically, if we were to go into this mathematically, we can say if the value that we get from here is 0.35, well, this is going to activate this axon terminal. Or if our value is, say, zero point 0.5, then it's going to access this terminal. And so deep learning works in this way. And we can think about this more. And in this section, I'll talk a bit about some of the different deep learning methodologies, but I won't go into as much detail as the traditional methods just because this could be a whole nother talk. So maybe we can convince Ryan and Caleb to bring some other expert to talk about and give education series on neural networks. But as I described, we think about our inputs as the dendritic portion of the neuron. We've got two images here, say a dog and a cat. Well, if we feed this neural network an image of a dog, it's going to have these inputs, and based on our weights and biases or sums and our F function or activation function, it's going to light up certain portions of the neural network. And from that information, we get this hidden input layer, which I won't describe into super detail, but it's one of the reasons why neural networks are considered black box, as well as one of the portions that makes these architectures so complex. And once these light up, then that's going to send another signal from activation function and say, okay, is this dog or cat? Well, in this case, dog, because we gave it a dog input. So you can see it a little bit more clearly here how the neural network architecture works a bit like the human neuron. But you also have other forms of neural networks, such as convolutional neural networks, or as are commonly uh, denoted as CNN. So you might see CNNs quite often. And these are a little bit similar to the neural networks, the artificial neural networks, and that we also have inputs, we've got hidden layers and nodes, and we've got outputs. However, one of the biggest differences is convolutional neural networks use three-dimensional data, so images, so for image classification and object recognition tasks. And again, I won't get into the very specifics or many details for CNN, but one of the ways that it works is it takes your input image, it applies different layers of filtering, and it extracts these features from those filters, hence this feature maps. And it can do that as many times as you tell the architecture to, and compress it, and you finally get some output. So convolutional neural networks are really great, and especially when you're working with image data. And so this is one of those cases that I mentioned briefly at the beginning of this talk, where maybe you don't have a ton of image data, but because of the way convolutional neural networks work, there's still probably going to be a better method for people who work with, say, hyperspectral data or drone imagery. They're very powerful, even if you don't have, say, tens of thousands of data points or a million data points, just because of the nature of the way this works. And then we also have recurrent neural networks, which are really very similar to our artificial neural network. So going back to this GIF here, you can see it's very similar in that we have our input layer, our hidden layer or layers, and then our output layer. However, one of the key differences is in one of the input layers, we actually go back to another hidden layer, hence this recursive process, and we can make a prediction based on, say, a past variable or the two past variables. So they're really, really powerful for making predictions for sequential data. You can think of forecasting, for instance. So recurrent neural networks are really great if you're working with forecasting or backcasting, which might be even more useful in astrobiology when you're working with, say, sediment cores or something like that. So you can see just from these three major classes, and these can be subdivided even further, deep learning and neural networks are quite versatile. But again, they're very computationally expensive, and they often do need a lot more data than our traditional methods. So it's something to consider. So unfortunately, or fortunately, depending on what you like, um, the supervised machine learning doesn't stop at just picking your model and developing your model. You also have to evaluate your model, which is a little bit different than our unsupervised portion. And there are different ways in which you can evaluate your model. I won't go through all of them because like there's so many different ways that you can evaluate them, but I'll just describe some of the more popular methods and methods that I think are going to be more useful for understanding how they work. And so, depending on if you use classification or regression, your model evaluation is going to be slightly different. So, for classification, one of the most popular ways of evaluating your model is by computing a confusion matrix. And as the name suggests, this confusion matrix basically is a way to understand and evaluate how confused does your model get. Um, more more specifically, how well is it able to classify data correctly or wrongly? And so there are different metrics that you can compute from a matrix, including accuracy, which we are all, or most people probably are familiar with accuracy, precision, and recall. And we can think about this more visually as well. So on the bottom right here, we've got an image of a confusion matrix. So in this case, let's say we have a binary classification. And by binary, I mean just two outputs, output A, output B. The way that you can read a confusion matrix is if we look along the diagonals, these are going to be your correctly labeled uh, classifications. So true positive, or let's just say class A, or true negative, class B. And then we can get some other interesting metrics such as false positive, FP, as it's often called, and false negative. Well, we can compute the accuracy of our classification model by basically taking the sum of our correctly classified labels, so true positive plus true negative, over the sum of everything. And so in an ideal world, this would be 100%, and this would also be 100%. But obviously, that's not always the case. Precision and recall are similar, but not quite the same. And the best way to think about precision and recall is how well is it at classifying a particular class. So for instance, for precision, if we have class A or true positive, how accurate is the model at classifying true positive? So if we have class A and it predicts class A, how likely is it going to be that class A? So for the higher the precision, the more likely it is that when the prediction gives a particular class, it is going to be that class. And recall is similar. However, it just uses slightly different mathematics. And so you'll see this in the Python walkthrough tutorial that I'll discuss in just a bit, that we don't always want to use accuracy, even though you often see this metric uh, indicated or people often report this metric. This is not always the best metric to use because of the fact that we are often working with multiple classes. So it's precision recall are going to be a lot more important, especially when you're thinking of multi-class or imbalances, which I'll discuss a little bit later too. Um, oops. So then you also have loss function, which are going to be how you evaluate model performance for regression. So basically, a loss function is a mathematical function that measures the difference between a model's predicted value and its actual value. So there are multiple different metrics that you can use, and for the world of astrobiology, most of us are probably familiar with coefficient of determination or your R squared value. You also have your mean squared error, your root mean squared error, mean absolute percent error. And depending on what your data looks like, you might want to choose one metric over another. I won't talk about, unless people have questions at the end, I won't talk about why you would want to choose one over the other because it's really data dependent. However, I will say that the three most common are going to be your coefficient of determination, mean squared error, and root mean squared error. But sometimes you are interested in these as well. And I won't go through the mathematics here, but I will put these up just so that you can see how you can compute the coefficient of determination and mean squared error, root mean squared error. So here we've got our equation for r squared to the right, where we take 1 minus the sum of our our observed values, y, minus our observed values, or predicted values, y hat, sub I, and we square that, and we take we divide that over the sum. And mean squared error looks slightly similar, but a little bit different, in which we're actually just taking the mean error of this squared error. And then the root mean squared error is basically the square root of the mean squared error. And you don't have to necessarily know or understand each of these equations, but one thing that you'll notice is in all of these equations, you're determining some error. And you'll almost always see this in most, let's say, machine learning papers that are describing their loss function, is you kind of always want to look for this yi minus y hat I. That's going to indicate how they calculated their error. And there are reasons and justifications for why you might want to use one over the other. There's also learning curves, which is a really great way of evaluating how well your model is at actually learning. And so here we've got two cases of different models and their learning curves. And we can see here this blue line is going to indicate our training set, and this yellowish green line is going to indicate our test set. So in this particular learning curve, we see how as the number of training set size increases, our error also increases. That's maybe not something we want. We kind of want that to be low. And then our test set is going to be decreasing in error. And so it produces this low gap, but we still kind of have a high training error. On the other hand, we might have a case where our model has low training error, and our testing set also decreases a bit, but it's still quite high for its error, and you have this large gap. So the way that we can read these learning curves is, well, when there's a large gap or large discrepancy between our test set and our training set, well, we are most likely going to be overfitting our training set. And then if there's a small gap but a high training error, well, we're perhaps underfitting because we can't learn from our training set very well. And so a good model is going to have both low training error and a low gap. So in a good model, we'll have our testing set go something like this. So learning curves are really great, and I'll show that as well. So those are some of the most fundamental aspects of supervised machine learning models, at least from my opinion. And so for this last portion, just like the unsupervised learning part one, I'll just give sort of a truncated Python code walkthrough for employing supervised machine learning. So the construction of supervised machine learning consists of this general architecture. So this is not always going to be the case, but most machine learning supervised models are going to follow this particular architecture. More specifically, we'll take some raw data and just some Excel spreadsheet or CSV file, or perhaps images if you're working with hyperspectral data. We take some raw data and we employ some type of pre-processing. Pre-processing can include things like dimensionality reduction, just to eliminate the number of features for computational power, or maybe we are employing some supervised machine learning or semi-supervised machine learning method in which we use a clustering method as a way to produce agnostic classes, for instance. There's also scaling, standardization, normalization, encoding of categorical variables. So a lot of times for these traditional models, it has to have a numerical input, so we can encode categorical features into something that's numeric. But there's a variety of pre-processing techniques that you can use. And there's many people who even just study pre-processing methods. Once we import our raw data, pre-process our raw data, then we can construct our model. Classification, regression, depends on what your question is at hand. And then, as I just mentioned, we'll evaluate our model. Is it good? Is it bad? Or is it okay? And from there, we can decide if we want to tune it, hyperparameter tuning, as we call it in machine learning, and make it better. And then maybe we want to extract some features. Why did our model make this decision? Which features are going to be most important? So one thing that you might notice from this architecture is that, well, model construction, which sometimes we're all very excited about, is actually just such a small portion of supervised machine learning. You spend most of your time in the pre-processing stage and post-processing stage, and then feature extraction depending on which model you're actually using. And so you may have heard the term garbage in, garbage out, and that's why these steps are so important, because you want to have the best inputs into your model before you make your prediction, or else your model is not going to be very informative. So now we can think about applying this to real-world data. So recall from last time in our unsupervised learning method, we were able to detect patterns within our data set from both the standard PCA, or linear method, and our T-distributed stochastic neighbor embedding, or t-SNE, or nonlinear method. We can see that the unsupervised portion was able to cluster our data into, say, different groups of total organic carbon percentage, high, medium, and low, perhaps. And because of the fact that we showed that the t-SNE performed a little bit better than our PCA, it was likely that there were many nonlinear relationships in this data set. So using the groupings from our unsupervised learning, let's see if we can predict total organic carbon abundance using supervised machine learning. And so because of this information that we got from our unsupervised portion, nonlinearities, and these groupings, for this coding portion, I'll mostly discuss random forest. And again, that's just mostly because of the nature of the data being having more variables or features and samples, as well as the fact that it's nonlinear, and random forest is really great with nonlinear data. And to make it easier, and we're going to first talk about classification, we'll group these total organic carbon into high abundance, medium abundance, or low abundance. And so that's what we'll talk about going forward. So similarly to our unsupervised portion, we also have to initiate our model, develop our model. So like last time, we'll tell our code or our program, in this case, Python scikit-learn, we'll say our features from our data are these particular columns, and our labeled or our target is going to be this Y. And so once we define what our features are and what our target variables are, so high organic carbon, medium, or low, we then have to divide our data into training and testing set. So this is something you don't do in unsupervised learning, but very important in supervised learning, because dividing our data into testing and training sets is how we can actually compute our model performance. So now that we've defined our variables, denote with the percentage of our test size and our training size, we can then set the model by using a very simple function. So in this case, random forest classifier. If we were going to do regression, we'd use random forest regression. If you want to do support vector machine, you'd use the support vector classifier function. Theoretically, we can just use all of the default options, but that's no fun. So we'll input some of our own hyperparameters. So the n estimators is going to be a hyperparameter that's very important for random forest. Basically, that's how many variables you're going to use. Your minimum sample split, thinking about the decision trees, that's how many times you're going to split, and then whether or not you're going to rerun those bootstrapping. And so those are just some simple hyperparameters that we'll use for random forest. And then we can also determine the random state. This is just for reproducibility. Once we define our model and its parameters, we can fit it by taking the training set, so X train and Y train. We can fit that to the model, make some predictions from our test set. And so this is going to tell our model, was this right or was this wrong? We can repeat this multiple times and get some cross-validation score. And once we do that, we can actually define the metrics from this model. And right now it looks pretty good, right? We've got really high precision, 1.0, 9.5 for low category, moderate category is 0.85, and our overall accuracy is 89%. Well, okay, well, things don't seem to turn out as they actually are, because despite having a high accuracy, we see that this model did very well with classifying moderate data, moderate total organic carbon, low organic carbon, and it actually did very poorly with high. And also, we kind of have this really large imbalance, right? We only have 5 data points, which you can see here for our high class, and we've got 20 and 30 for low and moderate. So even though we have this high percentage, it's not what it seems. And this is one reason why having a confusion matrix can be really important for evaluating your model. Because if you just report this number, well, you're making some perhaps false claims. So we can overcome this, at least for this purpose of learning, and sometimes you do want to employ this actually in your research, is we can do some data augmentation. So basically make some false data within reason of what our features actually show. And we can use this by doing a technique called a synthetic minority oversampling approach. In this case, SMOTE, which is the function that we can use here. We can fit this function SMOTE to our data set, get some basically produce new data, augmented data within reason of our data set. And we can redo the same thing, denote testing, training, and then rebuild our model. And we can see here that we get something a little bit better. And this is just for the purpose of teaching. And so maybe you would want to interrogate this a bit more. Going from 2 to 5 to 30 and 0 is a lot. But just for the purposes of teaching, we can see here that our model looks much better now. We don't really have a class imbalance. All of our classes are high, low, and moderate are very similar in terms of their number, and we have a very similar accuracy. So although our accuracy didn't improve that much, went from 0.89 to 0.9 or 90%, we can be more confident that it's not going to be overrepresenting some classes. And I just kind of went ahead and also computed one for a support vector machine. And I should mention that I use the kernel trick so that we can get something a little bit more close to our random forest. If I did the linear method, we would not see that. And if you want to play around with the code that I think Ryan provided, you guys can actually see the difference. But using the kernel trick, we see that, okay, we can get performances that are very similar. And so this is where learning curve comes in. So if we were just looking at these two models, we can say, well, okay, let's just go with our support vector machine. It's a little bit better, 91% versus 90%. Well, when we plot the learning curve of this data, we can actually see that the random forest is maybe going to be the better model to continuing to work on. So neither of these models are perfect, but we can see firstly that both models are learning. So as we increase the number of samples in our training set, the accuracy of our test or validation set is improving. This is true for both support vector machine and for the random forest. However, one thing that we see is the training class for support vector machine is not as great as the training score for our random forest. Additionally, for both models, we do see this pretty large gap, and large gap actually really depends on how one defines it. In the case of astrobiology, maybe 11% is not actually that much, but for this case, let's just say it is a lot. 11% difference between our test set and our training set. And in this case, okay, maybe there is about 5%. However, one thing that you'll notice is the support vector machine seems to plateau, maybe right around 200 samples, where the random forest, if we take the error around these points, it's is not quite at the plateau point, which means it has more room for improvement if we add more data to these models. But we also, knowing that we've got this large gap and just looking at the behavior of these learning curves, both models can definitely benefit from some hyperparameter tuning as well as adding more data. At least our random forest can benefit from it, adding more data. Support vector machine, maybe not. So once we develop our model, we can then, and say we're happy with it, we can then predict it on new data. So in this case, I'm just generating some random data. You don't really need to know this code at all, but this is just generating some random data. And then using the function predict.proba, we can make predictions of new data sets. And then we can basically get some probability distribution of the different classes. So let's just say, for instance, this class, this sample here, LCLD 5. Well, we can look for the highest probability, and in this case, it's 71%. So we can say that this sample is most likely going to be low abundance versus this high percent or high concentration, which is 5% versus moderate. But maybe you have cases where it's closer to 50% and 30%. So maybe you might not say that it's most likely low, but it could be both low and high. So anyways, this can be really important for when you want to probe and think about your data after you make a prediction. I won't go through this just for the sake of time, but we can also employ regression. And as I mentioned before, we can change our random forest classifier function to regressor, basically keep all of the other hyperparameters the same, and we can produce some regressive model. And unlike the classifier, which we use confusion matrix, we can look at the root mean squared error for this and see that it's within 2% total organic carbon, which is pretty good. And so, yes, kind of breeze through those last couple sections, but to leave some time for questions, that is it for me. But also, I want to make sure that, machine learning has been improving a lot over the last couple years, maybe 3 to 5 years. And so there's a lot of resources now. The Journal of Geophysical Research just produced a journal like last year called JGR Machine Learning and Computation. So this is really great for if you want to think a bit about some more advanced topics for machine learning and geoscience problems, as well as astrobiology. And then obviously the resource that Caleb and Ryan have put together at NASA. And yeah, so with that, I'd like to thank you for your attention, and thanks for Ryan and Caleb for giving me the space to sort of hopefully educate you guys a little bit more on supervised and unsupervised learning, and I'll take any questions if there are any.
Awesome. Thank you so much, Floyd. So just real quick, since we're a little tight on time, if you have a question, raise your hand right away and we'll get you, but also feel free to post it in the chat and then I'll collect them and get them to Floyd and then we can get back to you on email. So are there any questions right off the bat? Give people a second. I have one, but I want to give the audience a second. Okay, well, people might be typing them. So Floyd, let me find real quick. I had a question. This is probably very simple and kind of dumb. When you were talking about random forest way back at the beginning, you were showing how it's almost like a voting, like A and B, and then A1 because of a majority. So is it always a simple majority? Is this something that's tuned where you could have it be something like 66% or 75% before something is essentially voted in? And how do you not end up with ties?
Oh, okay. So both good questions. So if I'm understanding your first question correctly, you're asking your first question, were you asking if you always have to have 2 trees or 3 trees, or and then if so, with the voting, does that?
I'm just assuming, right, I'm assuming you have to have at least 3 trees or more, or at least something so you have some kind of, like yes or no, or like A and B, so you can have a majority,
Yeah,
like a
so
majority vote.
in most cases, yes, you'll have to have more than 2 trees for sure. And that number is basically the number of trees is a hyperparameter. for random forest. So I didn't go through it here, but you can employ, say, hyperparameter tuning for your model, run, say, like a search grid for your best parameters, and that can tell you how many trees you should use or at least start with. That way you don't have to just pick a random number. If you did want to say just use a single tree, then that's just a decision tree. So random forest is technically an ensemble model of decision trees, which just means it takes multiple models, specifically a decision tree model, and it takes the results from both. So yes, if you want to just use one decision tree, you could, but it's usually just going to be less accurate than a random forest. Does that answer your first question?
Yeah, it does. Yeah.
And then what was your second question? Can you restate that?
Yeah, it was about the does the user tune essentially how many I guess like how much agreement there needs to be before you have a final result? Because like here, you've got AAB.
Mhm.
So what that would be like, 66%. But what if it was, is that something tuned or do people just expect a simple majority?
So in most cases, it will be a majority. You can say um, you can print a probability distribution table, sort of. It's not quite the same, but it would be similar to um, this table here, but specifically for the random forest trees. So you can get more information about that for each decision that it makes. That's usually most people don't tend to do that because that can be a lot of work. In most cases, you probably won't get a majority vote, but you can interrogate the trees more. But most people don't do that specifically just because of how much work and effort it is. But you can theoretically do it.
Okay,
Well,
we have let's get this can you see any of the questions in are you able to see the chat float? I always forget.
no, when I'm sharing my screen, I can't see the chat.
Okay, so I'll read it. And actually, for everyone else, real quick, I understand we're at the top of the hour, so feel free to drop off. This is recorded and can be reviewed along with part one on our seminar page and on our portal and on the YouTube channel. But Floyd, let me read this real quick and then we'll finish. Could machine learning produce mathematical expressions? For example, in response to data of exoplanet distribution, can machine learning algorithms then re-express that data using mathematical algebraic equations?
Oh, yeah, definitely. That's a really great question. That's actually kind of where a lot of machine learning is going in the geosciences and astrobiology. And so that specifically is going to be called theory guided data science or knowledge guided, knowledge driven data science. And so basically, sometimes you don't want to use a machine learning to make a prediction for everything, because, say, with exoplanetary research, I mean, that data set is already quite complex. So sometimes you might want to employ supervised machine learning to maybe determine or predict some parameter of a differential equation, which you can then feed in. And so they kind of work in tandem where you've got your numerical model, and then you can use your supervised machine learning model to predict some parameter from that model to make the computation power a little bit less expensive for both the machine learning as well as, say, numerical model. Um, yeah, I don't know if that answers your question, but if not, I can answer it a different way.
Uh, Ali said thank you, so it looks like we're good there.